All right. So the plan is to do more nonsense with PureScript, but just gotta let my cat in. Right. Let's see if this works. I switched up the layout a tiny bit. Just make sure. All right. Wait, what? Where's the stream over? No, the stream is not over, is it? It's saying we're offline now. That's weird. The microphone is right too far in the back. All right, that seems like we're live. Looks good so far. Sound is all right. All right, cool. So I'll close this. And we can get started. So, all right. We're back. So yesterday we started writing WASM binaries, and today I'd like to continue with that. We messed around with buffers in Node, and we figured out that buffers are actually fixed size in Node. And so what I've been doing is I've been looking for some buffer type that grows dynamically, because what we do not want to do is basically allocate a huge buffer and then just write into that, but instead we want to use a buffer that can dynamically grow. And yeah, again, because Node doesn't actually provide that kind of a type, so the closest you can get in Node is to use an array of ints, but that's actually very far from a byte array, really, because, well, arrays are kind of expensive compared to the low-level stuff in Node, which is uint arrays, which is what we've been dealing with here, and really buffers are just leftovers in Node from before uint-array 8 was a thing. So we should try to work with uint-array 8s instead where possible. So the plan here then is to have, and I've already sketched this out, I've kind of was curious if this is possible to do in PureScript, and it's possible, but it's also kind of terrible. So I'm not quite sure if we want to use this kind of a thing, or if we're just going to implement the buffer part in JavaScript. I was kind of confused that I didn't see anything like this in, or like I didn't easily find one of these in NPM, but maybe I just don't know what to search for. You know what? I'm actually going to use this for now, and then we can still figure something out if we want later. So what I'm going to say is I'm going to make a new module. It's called dynamic buffer, because that's really what it is. It's a buffer that dynamically grows. Damn it. And, well, I don't actually have the FFI for this, I think. Maybe I should have put the FFI in here as well, because I wrote this on my laptop rather than my machine. Well, maybe we can figure the FFI out. It shouldn't be that hard. Why is this? Okay, now it works. So this is the dynamic buffer. I'm going to tell the PureScript language service to start right here. And let's try to create a file dynamic buffer.js, which is going to contain all the FFI for this module. So the FFI we need is this. Okay, so let's try to implement these. So export dot. And what is this? This is a function of 3 arguments. The first one is a buffer. Second argument is the offset, and the last argument is the value we actually want to set. I'm just going to call that one x. And then the task for us is to call, and this is really an array, so let's actually call it an array. So what we need to do is we need to say array at offset equal to x, like so. And then set all, it's going to look very similar to this one, so let's call it set all impl. Rather than setting a single value inside the array, we're actually going to call the .set function, which lets you set, it's basically a blit function, so it lets you paste a whole bunch of values into an array starting at some offset. And I'll have to look up the API for this because I do not remember in which order these arguments go. Just gonna comment this one out real quick. Okay, so let's try this, figure this out. So this is JavaScript uint8 array. There should be a set function here. So here we go. So set as its first argument accepts the array we want to store, and the second argument is the offset. So done that right. So we're just gonna leave this as is. So allocate is a function that takes a size and is supposed to return us a newly allocated array. And the way we do this is we just say new wait, how do we do this? New uint8, here we go. And we can pass it the length that we'd like, so we're just gonna do that. One new is good enough for us. So let's also implement subarray, which is a function of 3 arguments. The first is the array, we get an offset, and then we get a width. So this is the length really that we want to subarray here. And this is a view, so this doesn't copy any bits. It just gives us a view into the array. So let's just check the arguments here. So 1 is the offset. There we go. Okay, so we do array.subarray. This needs to be 2 R's from offset with length. We need to return whatever this returns. And the last thing, maybe that's not possible, maybe that wasn't necessary, but I decided to try and be as efficient as possible here, and so we have a boolean and an action. And the idea is that we are going to say, well, if the predicate holds, then we're going to execute this action. And while the PScript already has this as the when function, but I decided I'd try to make it a little more efficient. Maybe this isn't necessary, and we could just get rid of this. I think we should be good here. So let's see if this compiles. It seems to be compiling, so that's good. And now let's look at what I've actually implemented here. So this is just the a bit of FFI bindings to the typed array API in JavaScript, really. And so what we have here is a dynamic buffer, and I've kind of been inspired or copied the implementation of buffer in OCaml. So if we go into the standard library for OCaml and look at the buffer file in here, you'll find that it has a record type inside. So a buffer in OCaml is a thing that has a mutable bytes array, and that's this thing. It has a mutable position, that's this thing, and a mutable length. And in PScript we need to use refs if we want to have mutable properties. It's a lot less ergonomic to work with than in OCaml though, because the whole effect tracking kind of gets in the way. So that's why I was considering just writing this in JavaScript, but now that I've already written all the code, maybe that's good enough. So really what this does is just that it gives you a buffer of a certain size, and you kind of try to get something in the order of magnitude that you expect the final product to be in. And when you hit, like basically when then you start writing stuff to it. And once you hit the limit, so once the buffer is full, you just allocate one that is twice as large and fit the extra data in there. And then I've added these two functions. So add int adds, or like add int 8 here, adds a single int in the range of ASCII. So this should actually be, yeah, because that's 0 to 255. So that's what you can fit into 8 bits. And well, if we're outside of that, we need to throw it out of range error here, or we're going to get some weird failures. And I'm going to we resize it over here. So we say the buffer needs to have space for one more element. And then we just write that element at the position. So that's the set impl bits here. And then we just track how many elements we've written. So this does the offset tracking. That was kind of annoying in the stuff we had before. Right. And so this is the buffer class that I've come up with for dynamic buffers. We're probably going to need to add a few more functions, but I don't think we need to add too many more. I think this is good enough. We should make sure it works though. So I've written this, but I haven't really tested it much. So let's try to do that now, I guess. So one thing we immediately see is that there's this write to file here for buffers, and we have not implemented that for our dynamic buffer. So how do we implement that? So write to file dbuffer, and then this needs a string as an argument, right? Because that's the file path. It's going to return an effective unit. And write to file takes a path and a dbuffer, like so. And what do we need to do here really? So I'm going to say we're going to need to do write to file impl on buff.buffer. This is going to take the path, and we're not actually going to pass it the buffer because that's a reference. So we first need to read that reference and say that's the buffer here. And then we're going to pass that out. And we can actually, that's actually called bytes. And then I'm just going to see if we can use the implementation we use for buffers. Because if I have a okay, so well, we're just going to put that in there for now. Of course, this is not going to work in again when you try to do this from within the browser. This needs to be write to file impl here, and this is going to be a function that takes a path, and it's going to return as another function that takes the bytes. And then it's going to do this basically. So write file, oh yeah, and it's going to take a callback as well. So okay, we might actually end up wrapping it up like we did with the buffer, I think. So let's do that. So let us do that. So we're gonna use this type, just that this takes not a buffer, but instead it takes an uint8 array. So uint8 array. We need an import for nullable, and we're gonna need an import for error, like so. And then this is actually gonna be our function that takes a dbuffer here, like so. And we do need to take the callback, So this is the debuffer. Now what we're going to do is we're going to get out the bytes by reading buff.bytes. We are going to pass those bytes in here. And we're going to need to import maybe, and we're going to need to import this one. And we're going to need to import this one. Okay, and that does type check. I have no clue if it actually works though. We probably actually need to copy this implementation instead, because this is the non-curried one. And we're going to need to say that fs is equal to require fs, like so. Right. I'm actually interested in why this is, well, if this is all written like this anyway, this might as well be an effect fn3, right? And then we can just do this, this. Now we just need to say run effective n3 here. And then in the FFI, we can be a little less verbose here. We can just say that that's actually what we're doing, like so. Or to make it more uniform with how we did the other stuff, let's just use good old ES5 syntax for function definitions, because that's good enough in our case here. Okay, I think that should be good enough. Let's see if this compiles. So npx spago build, and it does not compile because we need to add a couple of imports here. So we need array buffer types, I believe, and not like this, and we need refs. HKK represent. So let's format this halfway decent anyway. Like so, and we're going to indent this. Let's say about one more. Okay, like that. And hopefully if we run this again, okay, now things succeed, so that's good. And we're going to get rid of this glob for tests because we have not written any tests. Okay, looks good, sounds good, compiles. Let's check out the main, where we used to use our buffer module, which I'm hoping to retire, and we're going to use the dynamic buffer instead here. So now these won't work anymore, so let's try doing this one again. So we're going to create one, and we're going to say that this is also going to have space for 8 bytes. And then all of these, write uint is not what this is called anymore. Instead, it's add int 8. So add int 8, like so. And this is the actual buffer here. And then what's this one over here? Oh, I need to add an import, so let's actually do that. So dynamic buffer, not an import, but an export instead. So we need to add the export for write to file here. Here we go. And all of these functions no longer need to take an offset. Switch to Cocoon. But why? Can I script Cocoon in Lisp? Because otherwise, that's not a language for me. All right, so should be able to run this now. another successful WASM module out, so the dynamic buffer is working. Good morning, Sharptical. How's it going? Hope you're doing well. I'm gonna now create a buffer that is a little too small, so this has to resize, and it still creates a WASM module, so that's good. So now we have a dynamic buffer type that dynamically resizes as we add more and more bytes. I don't really have a goal yet. I'll think of goals once we are in territory where I know what I'm doing. Right now I'm just messing around. But what I'm working towards is having a data structure that lets me write an encoder for the WASM binary format, right? And so really what I've done here is, now that we have a dynamic buffer that resizes as we add more data, we have a data type that we can use to give ourselves a little nice DSL for writing out the bits that make up a WASM module. Another thing I've done since last episode is that I actually looked at the reference implementation of WASM, which is written in OCaml, and it has a full encoder for the binary format in 520 lines. So hopefully we can get something that does something in about 100 lines of encoder code. We don't need to cover the full spec after all here. We just need to cover enough for maybe calling a, maybe let's try to write a single simple function and have a WASM module that exports that. Right. Exactly. So I'd say we can, now that we have the dynamic buffer and we can write individual bytes, we can start by doing a few things here. So I want to start and write an encoder. So let's call this WASM encode. So I want to start by writing an encoder here, really. And I'm going to create the WASM .encode module here. And so I'm thinking we're going to wrap up some monetic stuff here. Maybe it's not worth it yet, and we should just work with functions for now. Let's make a non-monetic DSL first, or like a non-monetic set of functions, and if we want to make a DSL out of it, we can do so anyway. So we're certainly going to want the dynamic buffer here. That's the whole point. Like so. Oh, import. Like so. Here we go. And let's start by looking at the spec again. So once more, and I think we looked at this yesterday, but let's do it. Let's look at it again. So really, a module is just a sequence of sections, and all of these sections have special IDs. And really, this is all the sections we can write. We need to start out with a magic sequence of bytes up here, and the version of the WASM assembly spec that we're using. And you can leave all of these modules empty, which is what we're doing right now. So all we're writing is the magic bytes and the version. But what I'd like to do now is maybe we can start. I would like to create a WASM module, really. And I'm going to put this in a comment because it's going to be a while until we can get this. But I'd like to be able to write a WASM module that defines a func. I'm going to call it add10. And let's use add10, which accepts a parameter x of type i32 and returns a result of i32. And we're going to need to prefix this with a dollar. In the WASM, those are all just going to be numbers. So the textual format has these identifiers, but the binary format is just a bunch of indices. So really, this is going to be 0. And then what we're going to do is we're going to get the local index at index 0, which is going to be the first parameter. This has been passed, and we're going to try to put a constant on the stack, and then we're going to add the whole thing up, right? And then one more thing is that we want to add an export, and I don't even remember how that works again, so let's just look it up. So that's inside source. There should be a WAT file here. There we go. And that's what an export looks like in WebAssembly, like so. We're going to export add name at 10. And really, again, this is just going to be another index, right? Because this is going to be the function at index 0. And we'll see that we actually need to write a few more sections because the textual format is a little more concise here than the binary format. It's got a few things implicit that really aren't. All right. So when we start to look at these things, we need to figure out what all of these sections look like. And so WASM specifies, well, for one, there's all of these indices, but I think we can probably figure this out when we figure out what sections to write. But really, if we want to write a section consists of a section ID, which is 1 byte, the U32 size of the contents in bytes. So this is how many bytes does this section have, and then the actual contents. And this size of the contents is the size of whatever we write here. So let's just see if we can. I'm going to continue using snake case, which is not idiomatic in PureScript, but I've kind of gotten used to it now, and it's not like this is really a library I want to publish anytime soon. So, okay, so let's figure this out. We want to write the section. I'm going to start by saying we're always going to accept a debuffer as an argument, because that's the buffer we want to write this section into. Then we're going to take a section ID, right? And really a section ID is just an int. And then we're going to take, and this is where I'm already going to be kind of devolving from what the spec says. So now it says we should write the size of the contents. But if we want this function to be useful, we kind of need it to keep track of the positions. So that's a follow. Unfortunately, it's so small. Has followed. Thanks for the follow, mate. So where was I? Right. I want to actually accept an action here which writes. So this is going to be a function that accepts a debuffer, and it writes an effect unit, I think. Or maybe we're just going to accept an effect unit. I'm not quite sure. And then the whole thing is going to return an effect unit. So this over here, this argument, this is the thing that actually writes the section. So let's try to figure this out. So we're taking a buffer here. I'm just going to call it B because we're going to be passing it around all the time. We've got an ID, the section ID. I'm just going to call ID, and then we've got the actual action that writes the buffer. So we're just going to call that F. Okay. And so what's the idea here? The idea is that we're going to start by writing the section ID. So really we're going to just do debuffer dot add int 8. We're going to add the ID here. We're going to need to add a couple imports. Okay, so that works. So we wrote the section. What do we need to do now? So now we need to figure out, well, really what we want to write now is the size, right? But we can't write the size yet because we don't know. So I'm just going to say to do write the section size. But the problem is that if we were to now just call f here, right, so we're just going to write the section. Right, one thing we could do is we could say dbuffer dot, I believe there's a get position, right, so we can get position, right, and this is start of the section, and this is the end of the section, right, and then we could say the size really, well, the size is equal to the end minus the start, right. The problem is, once we call f, we've already written directly into the buffer, and really what we need to do here is we need to reserve some space, right? We need to reserve enough space to write the size. Well, and if we look at how integers, the sizes in integers, how integers are encoded in WebAssembly, that's actually not just writing 4 bytes, because integers are actually using a variable length encoding, which is called LEB128. And so we're going to have to implement that if we want to implement writing the size. Now, a variable length encoding would mean that we'd use variable lengths for the size, but we said here that we want to reserve the section size really and fill it in later, right? And so, oh, this is weirdly formatted. And so what we're going to do here is we're going to do a special thing. What we're going to do is we're just going to reserve 5 bytes. So I'm just going to call this reserve size bytes or something. And it takes a debuffer and it returns an effect. And here, I think we're just going to call this an offset. Did I export that? No. Okay, so this is going to reserve the 5 bytes we need for this buffer. And it's going to return us the position at which it has created those 5 bytes. Right? And so it's going to figure out the position. And then we're just going to write 5 bytes. Yeah, I believe this should be 5 bytes, right? I'm just going to add 5 of those. I'm just going to zero that memory out for now. And then we're going to say this is where you are supposed to, this is the start of the section. And so we can say here that we're going to reserve the size bytes. Okay, and this is the size offset. And we're going to get that by calling reserve size bytes on B. Okay. And then once we figured out the size, what we can really do is then we can go and write the size bytes, right? So write size, write section size, let's say. And the section size is going to accept the start where it's supposed to write in the buffer. So let's write that function next. So we're going to say, let's write the section size. And then we're going to look at how we actually need to write these bytes, because that's not going to be easy. It's going to involve some bit trickery. So this takes a buffer, an int, and an int, which is the size, and it just writes into the buffer. So this returns an effect unit. So we get in buffer, we get the offset, and we get the actual size. Okay, so now what do we do here? Right, so what this is going to be is it's definitely going to involve us writing 8 ints, but we can't just add them to the end of the buffer because that's what we're doing. That's not what we're doing here. Instead, we're going to be patching some bytes directly in the buffer, and I don't think I have a function for that yet. Right, so this actually sets an int at an offset. Am I exporting this? I do, so that's beautiful. I can just use set here And set accepts as its first argument the buffer, then the offset, just going to be offset here. Now we're just going to keep going, offset +1, offset +2, offset +3, and last but not least, offset +4. Right, and what we need to write now is the LEB encoding of size. So let's think about what that means. I'm just going to say 0 over here for now, and then we're going to think about what that actually means by looking at the spec of LEB 128. So when we click on LEB 128 here, it actually leads us to Wikipedia, and really we're dealing with unsigned LEB 128 here. Okay, and really what unsigned LEB 128 does with an integer when you give it one is it's saying, well, give me an integer, let's say I want to encode 10, or in hex that's 0xa, 0a maybe. Okay, so if we were to look at this in binary, we could say, well, let's just say we had 4 bytes here. That would be 1, which is, I believe that's the binary representation of 10. So this is the 1 bit, this is 2. Okay, so this is the binary representation of that, right? Okay, and so so we need 4 bytes really to encode the value 10. And what LEB does is it first represents the number in binary, then at 0 extends the number up to a multitude of 7 bits. Okay, so we're gonna round it up to 7 bits. So this is now 7 bits, right? 3 zeros and 4 other values. Okay. And then we break the number up into groups of 7 bits. Okay, we just have a single group. Output 1 encoded byte for each 7-bit group from least significant to most significant group. So this is about in which order we write these. So this is least significant to most significant. So if you've ever dealt with bytes before, least significant means we start with the lower bits. So this is, if this was to be 10, okay, let's use a number that is a little bit larger. Let's say we had not 10, but let's say we had, okay, wait, let me count. 1, 2, 4, 8, 16, 32, 64, right? Let's say we had 128. In binary, that is this number, which, well, if you remember what we needed to do is we needed to split it into groups of 7 and then 0 pad, okay? So now we have 2 of these, right? But this is the most significant one because this one is a lot larger. Oh, sorry, we need to turn these into zeros. This one over here is a lot more significant than the one over here because this one, this 0, let's make this 129. This one over here represents the value 1, and this represents 128, right? And so the way we are going to emit this is that we are going to emit this group first. And they look the same. Just switch them around. Let's make it 130. It's going to make this a 1, this is 0, right? So this is the 2 over here, and this is the 128 over here. Okay, but this is 7 bytes each, so this is just 7 bits. So we're going to need to fill it up with 1 more byte. Sorry, 1 more bit to make this a full byte, because every byte is 8 bits. And so what does this say then? We add the high 1 bit, so on every but the last, so the most significant group. Now, if I look at this, from least significant to most significant group, if I look at this looks weird to me because this is not going from least significant, but this is going from most significant to least significant. Oh wait, it ends up emitting them in the other way around. Wow. Okay, so this is the groups we have. And then what we're supposed to do is we're supposed to add a 1 to this byte over here. So this one over here, only the first group does not get a 1. And if we had more of these, we'd, well, however many, the first bit essentially tells the decoder to keep going, right? Because we're going to emit them in this order. Right, and it's going to keep reading until it sees a byte that starts with a 0, I believe. Is that how it's supposed to work? No, it's going to write the 0, 1 last, so it's going to emit. Oh my, this is confusing. Yeah, we're going to figure this out by just reading a bunch of examples and then trying to emit exactly the value that they want us to emit to output. Right. Signed LEB is even trickier because then we need to deal with the 2 complement representation for ints, but I'm not willing to do that just yet. We're not going to bother with that for now. So I happen to know that the OCaml implementation does this somewhere. So maybe we can try to figure it out from that, because that's what's going on here. Right. And I think I can figure out what this does, but I already know that we're definitely going to need the bits module in PureScript because we're going to need to use logical operators on ints. So I believe that is data.int.bits, but I'm not, yes, it is. And exactly, so we're going to need and, or, XOR, these kind of things. XOR, hopefully not. Right, and shifts. So, okay, let's import that one. I am not sure if we have that yet. I'm just going to make sure we do. So we need integers as a library. And then let's make sure we have that. Just running a Spargo build real quick. Okay. So apparently that just added a bunch of stuff. So let's try to do this. So should we look at the implementation or try to figure it out from the spec? Figuring it out from the spec is kind of cool, but looking at the implementation is more likely to yield successful results. You know what? I want to figure it out from the spec. Let's try to figure this one out. So it's telling us that this is the way it ends up doing this. Okay, so what do we do? So we need to get, so what's the input we have? So we have this size, right? So this size is a 32-bit int, or at least we'd ideally make sure it is. We can actually do this in PureScript. I'm just going to say size equals s plus 0. And if we can look at the output here for WASM encode, dot encode index.js, we will see that in the right section, the first thing it does, wait, where was it? Over here, is that it ORs the thing with 0, which forces it to be a 32-bit int. That's how JavaScript works. And maybe there's an easy way of doing that or something, but we're just going to stick with that for now. Actually, in PureScript, every int is supposed to be a 32-bit int. So maybe that's not necessary, but we're just going to leave it in there. It doesn't hurt. Okay, so what do we need to do then? Then we need to break it up, and we're just going to say, well, we're just going to allow basically any 32-bit int value. So how many bytes does that mean do we need? So any 32-bit int value fits into 32 bits, right? Now, the LEB128 only gives us 7 bits of information on every byte, right? So we're going to need to divide that by 7, which is going to give us 4 point something, but means we can't fit it into 4 groups. So really, we're going to need 5 groups here, which means that we're going to end up with 35 bits of actual data plus 5 bits overhead, which is the added bit that tells the encoder whether or not to keep going, right? So that's why we end up with 5 groups here. Okay, so let's try to slice out the 5 groups. So really an int, wait, let me write that down. So that's what a 32-bit int looks like in binary. I'm sorry, like so. And so we want to slice out the individual bits. So the way you do this, and I'm just gonna, I don't know, just put ones somewhere in here, like so, just so we can figure this out. And so the way you get, let's say we just want this group over here. Wait, we need larger groups, right? This is not a 32-bit int. This is half a 32-bit int. This is 32 bits, right? Because that's 32 numbers. Okay, we're gonna split this up by 7 actually, right? Because we said we were gonna do that. So 1, 2, 3, 4, 5, 6, 7. Now we end up with 4, and I'm just gonna put these at the front. Not that actually 1, 2, 3. So now these should hopefully all be 7 numbers wide. I think they are. Okay. So these are all 7 numbers wide. And what we need to do is we need to get these groups out. So how do you get out one of these groups? Well, what you do is you say, I want to AND this. Right, so we use the binary AND. Then you AND this with a number that looks a little something like this. Right? Because what this is going to do is it's going to AND. So all of these are going to be 0 afterwards, because ANDing with a 0 gives you a 0. And if we AND these, only the ones that were 1 up here will be 1 in the resulting number. Okay, does that make sense? I hope it does. Now, what's the number in binary that has 7 ones in it? Right? So I'm actually curious, can we just type this into JavaScript and figure it out? I think we probably can. So let's try that. So 0b, which should give us the binary 1, 2, 3, 4, 5, 6, 7. So that's 127. Now what is 127 in hex notation? So 0x, and I believe it's 80, but let's make sure. That's not the number I would have expected, because I saw a different number here. Oh, what is this doing then? This is ORing stuff. It's ORing with that value. Doesn't that make all of this 1? Oh no, I see what it's doing. So what's the LSB? Oh, that's the fun part. Okay, yeah. Okay, I see what's going on. So this is, wait, that's 8 numbers. That's not 4 numbers, that's 8 numbers. So what is this doing? It is ORing the whole thing. Oh, I see what it's doing. It's ORing the whole thing by making this one a 1. So it's doing 2 steps at once. I just want to do 1 step at once, I believe. I don't want to do more than 1 step. Okay, so let's do 1 step. So we don't want to use a value this large because that's too large. We want the 127, which is so not 80 but 79. 7F, sorry. So that's 127. Okay, so let's say that the first of the chunks, so chunk 1 is going to be S, and now we need to use OR from bits, so bits.or. Like this, and I'm just going to add an import for that, hopefully. So from int bits, we're going to OR S together with 0x74. Okay, and that should give us just this bit. So what's this number in binary? That's 42. How lovely. And what's this number in binary? Okay, that's that. So that's a number. We're going to say, okay, this is the number. So 1,922. Okay, so 1,922. And what we said, what we're going to do is we're going to AND. Did I say AND? Yeah, this should be an AND, not an OR. So we're going to AND this together with 0x74, which gives us 42. That's exactly the number we were looking for, right? So that's the first 7 bits when we're going from least significance bits, right? And so we should be able to keep going like this, right? So we say, well, chunk 2 is going to be, again, we're going to end with that, but we need to do first is we need to shift the whole thing by 7 bits. So I believe there's a function here, which is going to shift to the left. Is that right? Or maybe we need to shift to the right? We'll try it out. That seems good enough. So we're going to shift by 7. Yeah, that's a very helpful signature. I need to figure out which one of these numbers is the one we're shifting by. I think is the second one, so this should probably be S, but I'm not entirely sure. So this is hopefully chunk 2. So really what this is supposed to look like is that we shift this whole thing. So we used the same number twice here, really, right? Didn't we? So this is just twice the same number. Let's make it a little more interesting. Let's add a 1 over here. Turn this into a binary number again. So this is now a binary number. Okay, so that's the number we care about. And if we go and say this number, okay, we can just use this, 0x74, that should still give us 42. It does. But now we're going to shift the whole thing by 7. I'm gonna guess that we need to shift in that direction. No, that's the wrong one. We need to shift in this direction. And that's 93. And I hope that that is what the first 7 numbers up here give me. So hopefully, if I did this right, I think we need these numbers. I hope this number is 93. It is. Okay, so that works. Okay, so we need to shift by 7 to the right. Okay, and then we're going to say that chunk 3 is by shifting this thing, and then chunk 4 is shifting by 21, and chunk 5 is shifting by 28. Okay, so that's all the chunks according to this thing, how you're supposed to do it. Okay, and then we are now, the last thing we need to do now is set the 1 bit on all but the 5th chunk. And to set the 1 bit, we OR the whole thing. Right, so this is a number which has zeros in every place but the last 7. We OR, and there's a, I think there's an operator for this. I think this is what it is, but let's just keep using the infix versions of these. So we're going to OR the whole thing with 0x80, and that's the number 1 larger than 7f, which is 7f is all ones like this, right? And if we give this just one more, we should be good. And we're gonna do this for every one of these. Yeah, sorry, Checkser, if I did think about this because well, I can't turn my brain off until the next stream, so I skipped a little bit ahead and read a bit more than I needed, so I kind of know what's going on here. Hopefully, we'll see if I know what's going on. So this should now let us write all these chunks. So now we should be able to say, well, I want to write the chunk 1 and the chunk 2 and so forth. And we just need to make sure that the last thing we write does not have the most significant bit set. So this should work, hopefully. We'll see. And then we're going to clean this up a bit, hopefully. Okay, so this writes the section size. Now let's how can we check this actually works? We can throw it at the WASM interpreter and hope it doesn't explode, but that seems kind of terrible. So let's try and see if we can make it produce this, maybe. Okay, so let's try that. So let's do that. So how are we going to check it? We're going to go into main. Do I have a print for this? Do I have a print function for debuffers? Let's make sure we do have one, because I don't think we have one right now, but we should have one. So dynamic buffers, print. Okay. So print takes a debuffer and just returns an effective unit. For now, anyway. We might make this smarter. So this is the buffer inside. And we're going to start by reading the bytes. Oh, that's not red, that's ref. By reading the bytes. And then we are going to say print impl bytes, which is going to be a function that takes a uint 8 array and returns an effect unit, like so. And now we need to go and add that function. So exports print. This is an array. And all we're going to do is we're just going to say, well, return function. Because there's an effect, we need to add an extra thunk here, and we're just going to console.log the thing, and maybe at some point we'll be a little smarter and make it a little nicer to look at. But for now, I think this should be good enough. Okay, let's try this one. So inside main, we are going to do a different thing now. We're not going to do any of this. What we're going to do is we're going to make a buffer. And we're going to make it, let's just make it, how many bytes are we going to need? We're going to use 40, right? 4 times 8. Yeah, let's use a few more just to be on the safe side. But I hope that we can end up with 5 unused bytes here. And then we're going to say encode dot write section size, I believe. Let me just add that import. That's wrong. So what did I call it? WASM slash encode write section size. Didn't I write that? I did. Oh, it did import. So the error now is a different one. So this should have a type. Okay, so this needs to write into the buffer at offset 0 the size, and now we're just gonna use this one. And I hope, I don't know, but I think, no, we don't have binary literals apparently, which is, can we write this as, okay, so what's that number again? If we just took that not that one, that one. So 0b, that number is 624485. Yep, exactly. That's that number. Okay, so let's put that in here. 624485. And we lost our offset. We want to write that offset 0. Okay, and then we want to debuffer print our buffer. And again, I think I have to go into the dynamic buffer here and just add an export for print. No, I did write that. Oh, it's still erroring because we didn't add the print impl function. At least that's what it's telling us. Maybe we didn't call it print impl when we should have. So yeah, we just call it print, but it should be print impl. Okay, so let's try again. So let's go and say Spargo run on the thing. Okay, so what did we get here? So this does not look like the thing I was hoping for. Maybe it does. Wait, that's 8 bytes, right? Maybe that's the number we were hoping for. And plus pimple. Well, that would be way too simple. So is that what we wanted, really? We wanted 4 bytes. No, I wanted 5 bytes to be written. But it's possible. It's very possible that the last one is 0 because it's too small a number. Now, can we look at these numbers in hex? Let's try to look at these numbers in hex, really. That's what we care about. So I'm going to use the browser again because that's the simplest. But it's tiny. Wait, I can increase the size and maybe you can also read this then. Sorry for being dumb on this. So what's the numbers we talked about? So 229. So that's the first number. So let's say 229. And then how do you turn that into hex? Well, we know what we expect, right? We expected for the first thing to be this. Does this equal 229? It does. So that's a very good sign. It's a very good sign. So the next number then is supposed to be this number, 142. Oh, things are looking good. Next number is 166. That did not work. Okay. So that is good. Oh, I know why it didn't work though, because I bet that all of these are zeros. Let's put this into binary. How do you, what does the number 0 be? Wait, no, that's not it, I believe. Oh, we need this number. Yeah, this number. Right. Like so. 0b. 38. Okay. So what's the number we're hoping for? 166. That's because we said we keep going here. And that's 166. And the next number is 128, which is just the one in front. And then a bunch of zeros. Right. Which is right again. And then we get a 0 because that's actually the point where we have all zeros. Okay, I think that's right. Let's try to put this output into, like, is there an online LEB thing or something maybe? That we could put that into. Online LEB 128. Not 127, 128. Not only online. Is there a online hex converter? Doesn't sound like what I want. Maybe. Is there an do we have, no, that's not what I want. Okay, whatever. I'm just gonna. Does the browser actually have an LEB 128? Maybe not. Okay, whatever. I think we're good. I think that looked right. So the numbers all matched up with what I expected, or like I was able to deduce what the numbers meant. And so I'm just gonna say, sure, that works. So let's see if we can get a little bit further. So encode over here. So I'm just gonna say that that works. And we can optimize this if we want to. Okay, so we write the section size. All of these things seem fine, really. Is this the correct way of measuring this? We get the position, and we, yeah, I think that looks right. So can we write a simple section? Can we write a section that does not need anything else? Let's see. So is there a section here which is so simple that it does not need a lot of stuff? So this looks way more complicated than I want. The function section, the problem is if we try to do anything in the function section, we need to add a bunch of other sections. The type checker can't do anything when you're just fiddling around with bits. I mean, we can, and we haven't implemented real LEB 128 as well in here, right? Because what we're supposed to do is, like in proper LEB, you only use as much memory as you need. But because we're statically allocating 5 bytes here, that's why we always write 5 bytes, even if the number would fit into 1 byte maybe. But yeah, I'm totally 100% sure that we're gonna have to deal with horrible bugs, and we're just gonna have to debug binary mess. But that's half the fun, right? We're trying to figure out how to do these things. So can we do the data section thing? It represents, decodes into a vector of data segments that represent the data component of a module. Well, that's terrible. Can we do a custom section which just does whatever? A name. How does a name work? What is a name? Names are sequences of characters which are scalar values as defined by Unicode. Sequences of characters. So how do you specify the length of this thing? A name. So it starts with a name, then a bunch of bytes. So maybe we can write a custom section here. The opposite of frame scope. Oh, okay, sorry. Oh, so I was having trouble with the internet. That's too bad. Sorry. So write custom section. We're just gonna do this for now. Right, and while we're here, we're gonna say make WASM module. That's a weird one. Let's actually move that function over here, because that's the header, right? So that's the magic header. So make WASM module, that's just write header. It takes the buffer as its first argument. All right, cool. Yeah, I mean, it's possible that it's just the two of us watching, really. Oh wait, no, we've got three viewers. Nice. Sorry, I'm back now. So just had to check my phone for a second. Okay, so we can write the header, and then we were supposed to start with the sections. And what I want to try is I want to just write a custom section, because those are kind of the simplest, and maybe we can just maybe we can just write a custom section here and have WASM interpret that, or like accept that. So this accepts a buffer, and then what does it do? It writes a section. I wonder what bit.fiddly safety could be done on dependent types. It's probably the same person encoding bits into types would really slow down the type checker. There's actually a bunch of languages that let you do this, but well, they're very special or like crazy. We're not doing crazy things here. We're just fiddling around with bits. So we're going to write a section, and the section ID is going to be 0 because all custom sections have the section ID 0. And then what's the section we actually want to write? So this is where we do the fun stuff. So we want to write a name. And so how do we tell how long a name is? A name is a vector of bytes. Okay, vectors. Let's figure out how to write vectors, because I don't think we've done that yet. So write vec, which this is, we're going to write a vector into debuffer, and really we're just going to accept an array of effect unit, I believe, maybe, and the whole thing is going to return the effect unit. So the idea is that these are all the elements in the array, okay, and a vector, if we look, is defined as their length, and then a code, oh no, encoded with U32. And so, I mean, we should be using the LEB120 encoding here, but yeah, we don't have one of those yet. So can we just abuse this thing for now? You know what? I have a feeling we can just yeah, let's just be stupid for now, and let's just assume that the number of elements is really small. So we're going to do array.length of elements. That's the number of elements. Here we're going to write a vector. And buffer dot set, not set, add int 8. We're gonna add, is there, what's an A again? We figured this out before, right? This is the header. So this is the whole 0 and then asm. So 61 x0 x61, I believe, is an A. So let's just try to write this section A. Let's import array.length. Damn it, all of these need to say just B. This imported from data foldable. I wanted to import from data array, please. Do I not have data array? Okay, let's add it to our imports. That's kind of surprising. I think it's arrays, actually. All right, that looks to have worked. So now this is an int, but it's supposed to be a, so this is the length, or like the number of elements. And so we're going to need to write that. And what I'm just going to do here is I'm just going to write the number, assuming it fits into 7 bits, because I believe in that case the LEB encoded value should look just the same. I think so. I think so. If it's wrong, we're gonna find out when WASM rejects this. So what's going on here? It's complaining that this has the wrong type because write_vec expects a buffer first. Okay, like so. So this is the name. So this is supposedly an empty section with a name A. Can we maybe, which one is S again? Let's use a nicer one. So 6 as I believe this is the, oh, this is actually, we need to be careful here. We need to write 4 zeros. 3 zeros, because this needs to be 4 bits. 4 bytes. Okay, so this is ASM, so 0x73. What bit level type checking were you thinking of? There's languages like, well, I mean, there's the low level stuff. I know that there's stuff like Verilog, for example. This is a language you use to compile to chipsets, and I believe this has all kinds of vector index dependent type nonsense. But I'm not an expert, so you'd probably find that there's probably someone on the Slack, on the FP Slack, that knows a lot better what kind of type level trickery you can do with these things. Okay. So I was like, I'd like to write the name, or like I'd like to write PS actually. So let's try to figure out what P is in ASCII. ASCII table. Okay, so what's P? P. So let's use a capital P. Capital P is hex 50. So capital P is 50. And then we're going to write capital S, which is going to be 53. Okay. And the hope is that this is going to work out, because the UTF-8 encoding of ASCII is actually just ASCII. All right. So now, can we write a can we use this to write a module? And here, this is actually, we're just gonna, let's actually accept the callback here. So maybe an error to effect unit. So this is when the writing the file fails potentially. So this is the callback. What we're gonna do is we're gonna say, we're gonna make a new buffer. So we're just gonna say dbuffer dot create, and we're going to say, well, it's in the realm of 124, which is way larger than what we actually need, but that's fine. I hope it's not entirely fine. No, because we're going to write a whole bunch of stuff that we didn't intend to write. So we need to actually change how we write the file. Yeah, let's change that real quick. So here, when we say that we write to file, we don't actually want to write all the bytes. We just want to write the bytes that are actually set. So set bytes, and that's going to be run effect fn3 subarray, not subarray. What's it called again? Yeah, I called it subarray up here, this one. Okay, we're just going to copy the signature down here. I was hoping it would show me that one. We'll get there. So what does it not like? Yeah, this is... Okay, so what is this? Do we still have a signature around? The ID is kind of failing here, unfortunately. So subarray, so it takes the bytes and an offset, which is, we're going to start at 0, and then how many bytes do we need to read? Well, that's the position of the current buffer. So we're just going to read that. And that tells us how far into the dynamic buffer we've already written. And then we're just going to use the sub array, which is the set bytes. Or like I'm going to say use bytes. And we just want to write those to the file, so we don't get a bunch of trailing zeros. That's the hope anyway. If that ends up working, that would be kind of cool. I'm not entirely sure if it does though. So that's fine. So we're going to write the header into that buffer, and then we're going to write a custom section into that buffer, and then we're going to write the whole thing to a file. So dbuffer dot write to file, and the file is going to be bytes.wasm, because I think that's the name we've been using for a while now. So bytes.wasm, and the callback is going to be the call. We're going to write b, and the callback is going to be callback. And we need to import maybe, probably, and we also need to import error. All right, so all these should work. So now inside main, I'm going to delete all that because we don't need that anymore. We're going to say encode dot write module, and the callback here is going to be, well, kind of the thing we had before. Do we still have that? No, don't, do we? Oh, it's below. Ha ha ha. So we do want this again, but it's going to be a little different now. So make wasm module is no longer what we do. We do encode dot write module. Okay, and then it says to not worry about these. Okay. We figured out how to write vectors, so that comment is no longer necessary. And then we try to run the file byte.wasm. I believe I've renamed that to bytes. Let's just be real. Let's just be sure. That's not the file I was going to look at. Encode source wasm encode. For some reason, my file finder is kind of broken. Maybe I need to add stuff to Git. So yeah, I wrote to the file bytes.wasm. Let's make sure we clear out everything that's called wasm in here for now. Okay. And I believe if we do npx spargo run. Okay, so here we go. Expected string length at +10. Okay, so what did we need to do? Expected string length at +10. So 10 bytes in. I mean, I'm pretty sure that's the when we're trying to write the length for this thing over here. Oh yeah, we need to, I mean, we're writing a length here, but then we also just need to write the whole vector. We didn't do that yet, so we're going to sequence elements like so. I'm just going to put that in the foldable. I'm not sure if that's going to work. We'll try anyway. So let's see what we're getting here. It's still complaining about expecting a string length. Now, how long is that string? That string's supposed to be 2 wide, right? So that's 2. Maybe I'm doing more stuff wrong. So we didn't click all the way through, I believe. So names. Sequences of characters. So char star. And char is defined as one of these things. Scalar values as defined by Unicode. That's terrible. How do I write one of these? Let's try to go all the way back. So we said modules. We said custom modules, which modules. Oh wait, are we not in the binary stuff anymore? No, we're in the syntax, but we need the binary format for modules. Okay, so here we are again. So custom sections. A custom section is a section of custom, and custom is name followed by a bunch of bytes. And name, as defined over here, is a vector of bytes, but it starts with a B first. So numbers are small. So a vector of bytes, and the bytes are supposed to be valid UTF-8 encoded stuff, but I was hoping that these 2 bytes make up a valid UTF-8 encoded string, but maybe they don't. Maybe they do not. So UTF-8 of char, if char is smaller than U plus 80. So what's U plus 80? I have no clue. U plus 80 is the padding character, which is encoded as this thing. But what's UTF-8 for U plus 53? Is that maybe, that's S, right? Okay, so that's S. How is that encoded in UTF-8? Just 0x53, right? So that should be good enough. And 0x50 is just this, right? Yeah, so those are the 2 bytes I care about, and I'm writing the length, and I'm trying to write the length as a single int 8. Is that valid? So what do we do? How do we do this again? We set the most significant byte on each byte except the last byte. We just want a single one of those. So we shouldn't set the first byte. So it should just, I was hoping that it would be able to encode this. So bytes.wasm is 7 bytes long. I'm gonna try to upload this to the online wasm disassembler, and we'll see what it says. Online disassembler. No, we're just going to use the online WebAssembly binary toolkit, so Webbit. Okay, and so there's an online wasm to wat. And we're going to try to upload our file here. So that's going to be script wasm, I believe. This one. We're going to try to upload bytes.wasm. Unable to read U28 LEB 128 string length. So yeah, we're failing to write. We are failing to write the length of the array. Now, can we just use this instead? I'm just going to copy this, which is going to look silly, but whatever. So we're going to write a U32 like so, and no offset here, just an int. And we're not going to set things by an offset. We're going to add int 8s here. So add int 8. Add int 8, no offsets, just chunks. And we're going to write this as a U32. I don't know if this is gonna work. I'm gonna try anyway. Well, it's not gonna work if it's an error. Where do we have an error again? In line 58. Why does this not complain? Did it not save or something? No, it's complaining. 58 over here. 58.1. Could not match up functioning with type effect because we're still accepting the offset over here. So we tried again. It's still failing to see the string length. Well, let's try logging it out, I guess. So this is a string length. Wait, how do you concat strings? Yeah, like so. Show length. And then do we have an import for that? We do not. Why is this not showing the errors anymore? Spawning child process. Resource temporarily unavailable. Okay, something's busted. Whatever. Can I add an import? No. Okay, so this is super broken. So effect.console as console. Okay, so let's try. Tell me what the string length is. String length is 2, which is how many characters I'm intending to encode here. And then maybe the problem is that that's not part. Maybe that's not supposed to be part of the section, actually. Let's see. Let us see. So a custom section. Delete all these. Okay, so here. A custom section is no, it's a section of custom. So all of this should go into the thing. So these should count towards these bytes. I think, yeah, pretty sure. So we're going to start out by saying we're going to write an ID. I'm going to write this offset. Going to start out with the current position. We're going to write F. We're going to get the position of the end, and then we're going to write the section size, but not at start, but at size offset. So maybe I was probably overwriting things that I shouldn't have. Oh no, that would be so dumb. And now it works. Oh god. Yeah, that pretty much tells you that it's time to stop. But just for the heck of it, I'm going to try and writing this one more time. So this time we're just going to write the length as it is, and this only works for lengths that are smaller than or equal to 127, but that's good enough for me. So okay, so it's telling me that parses as a that parses as a WebAssembly module. So now let's try and upload our bytes.wasm again, and I want to so that's just an empty module. Yeah, can I see the custom sections? Okay, so maybe there's more information we can get about a WebAssembly module from one of these. Wasm opt dump. Do I have that one? No, I don't. Do I have the other ones? That too. I do. So those are inside my bin directory. So where's the bin directory again? Over here. So it wasn't dash obj dump for our bytes module. Give me the headers maybe. There we go, and we have a custom section named PS, so that worked. All right, that's fantastic. I think this is where I'm going to end. This is all I wanted. So we're able to write a custom section into our WASM binary, and we're able to name it however we want, given that you only use ASCII, which encodes as itself in Unicode land. And so, yeah, that's pretty cool, I think. So this is progress. And next time around, maybe we can get to actually writing a function that does something. But for now, we've got a bunch of infrastructure that we're going to need when we try to do something useful with WASM. So, cool. Thanks very much for hanging out. Chatting with you guys is always fun. And I hope we can continue this tomorrow, but no promises. Cheers.